Hi everyone, my name's Chris. I'm a solution architect here at AWS. Who out there is a customer of Trainline? I bet there's lots of you because Trainline is an incredible company and is a household name for those of us here in the UK. Well, we have an opportunity now to actually hear from the Trainline about how they migrated to Amazon DynamoDB. So to start the story, I would like to welcome Jamie from Trainline. And Jamie, I'd like to ask, can you introduce yourself and tell us about the Trainline?
My name is Jamie Beaumont. I'm Director of Architecture and Engineering at Trainline and also Chief Architect. I'm here to talk about how we're using DynamoDB to improve reliability and scalability of our platform. But first we'll talk about a little bit about Trainline. Trainline is Europe's leading independent rail platform with over 5 billion in net ticket sales each year. Our purpose is to empower greener travel choices, connecting people and places. For all of you regular train users, well done, you're all eco-heroes. If you travel by train, you produce on average 7 times less CO2 than if you were to travel in car, and over 20 times that if you were to travel by plane. But how complicated can selling train tickets actually be? Well, it turns out more complicated than you'd think. So, Trainline are Europe's #1 rail travel app, retailing tickets for over 300 different rail and coach companies across Europe. We handle, on average, 3 million unique origin to destination combinations each month, managing the complexity of timetables, routing options, rail fare structures, and quota-based pricing. And we don't just sell train tickets either. We also deal with the complexities of real-time travel updates by integrating into the network. We're also not just a consumer business too. We offer rail travel booking solutions to businesses large and small, and we're also offer a white label train booking platform to the train operating companies. So here's some numbers that highlight our complexity in terms of our technology landscape. We moved to AWS in 2016, but largely this was a lift and shift to virtual machines, keeping our previous SQL Server estate largely intact. Once there, we went through a significant replatforming to a microservice architecture, as everybody does, ready for our IPO in 2019. But again, to reduce the risk of delivery, we largely kept our existing infrastructure and database technologies. One of our biggest recent challenges has been growth in traffic volumes, which have over doubled since pre-COVID. These volumes have been largely driven by the adoption of digital tickets on the network, but also the shift in flexible working practices, where people are buying fewer season tickets and more likely to move on the day walk-up tickets. The key number to remember of this talk is those 150 SQL Server databases, of which around about 40 were mission critical when we started on this journey. So on to our journey in leveraging the benefits of DynamoDB. Let's talk about our starting point. We had a suitably large maintenance overhead and had a large database team to manage these. Our DBAs were focused mainly on housekeeping activities and trying to optimize the performance to try and support the increasing scale of traffic volumes. These SQL Server databases became increasingly difficult to scale as traffic volumes increased and led to a number of significant stability problems. This culminated in a number of high-profile outages caused by database failures, and when databases fail, they tend to take a while to recover. Using SQL Server for everything meant that we're using it for things that it isn't optimized for, like storing large JSON documents and acting as complex search indexes. We've also had problems with the use of DynamoDB on the fringes of our stack, with instances of DynamoDB being used largely as relational databases. All of this led to a general desire to gain the benefits of platform as a service databases based upon collective experiences of these type of technologies in previous companies. So let's talk about our approach. Rather than allowing every single engineer to pick their own preferred database tech, we took a cloud-first approach and identified a single AWS native cloud database technology for each database type, allowing us to operationally harden and become real experts in these technologies. We identified a number of Pathfinder projects, bringing together product, database, and infrastructure engineering experts to prove out these technologies, with support from AWS to accelerate and help us along the way. We're now 3/4 of the way through a really punchy 2-year target to migrate 75% of our mission critical databases onto a mixture of DynamoDB and Aurora Postgres. That's around 30 operational databases, storing around 44 terabytes of data across the state. Chris, please tell me a little bit more about DynamoDB.
Yeah, sure. It's very interesting to hear about some of the challenges that Trainline has faced because they sound familiar to those of us at Amazon. We experienced something similar back in 2004. So if we rewind back to then, Amazon experienced a multi-hour outage during peak retail time. Our engineers performed a deep dive to find out what the root cause was of the issue, and our conclusion, even though we were running on what was considered to be the gold standard of relational databases for that time, we felt that we had reached peak relational database. A close look at how we used our databases produced some interesting insights. So the first is that for 70% of the operations that we were performing on our relational databases, we would use a primary key and we would get back a single row. For a further 20%, we would get a set of rows, but they would come from the same table. So for 90% of our operations on our relational databases, we were not taking advantage of the strengths that relational databases bring. So we embarked on a journey to build a new kind of database, a database whose strengths aligned to the 90% of operations that we were actually performing. That database would be Amazon DynamoDB. So what is Amazon DynamoDB? It's a fully managed, serverless, key-value NoSQL database. It's API driven. You create tables, you modify tables, you write data to tables and read data from tables all over a HTTP-based API. You use an SDK, the one that is for your chosen programming language, but it uses HTTP API requests. Under the hood, we've built a highly resilient, scalable, distributed system to service those API requests. That distributed system is made up of multiple components like request routers and storage nodes. The way to think about a request router is it's a node that receives your request and it understands where it should go and then it forwards it on to the relevant storage node. Storage nodes actually store your table data, and there are a huge number of these. A storage node holds a piece, what we call a partition of your table. But all of that's transparent for you. You see an API, we handle the rest. Today, DynamoDB is a tier 0 service powering most of Amazon. If that little bit of insight as to how DynamoDB works under the hood has gained your interest, there's a QR code here on the slide and a link in the description below that you can follow. That'll take you to a paper that was written by the DynamoDB service team a couple of years ago that gives you lots of interesting detail about how DynamoDB works under the hood. But let's explore what DynamoDB has to offer a little more. What are its core characteristics? Well, the first characteristic is performance at scale. When you use DynamoDB, you will get consistent single-digit millisecond read and write performance at any scale, with virtually unlimited throughput and storage. And we have lots of public examples of DynamoDB handling that kind of huge scale from customers like Amazon, but also customers like Disney+, Netflix, Dropbox, Snap, Zoom, and more. So again, I've got a QR code on the slide and another link down in the description. If you follow that, you can get to lots of our public examples of customers who are using DynamoDB in lots of interesting ways. What's the next interesting characteristic of DynamoDB? Well, it's secure and resilient. It's highly available by design. You don't think about availability zones or placing instances or having readers and writers and replicas. You create tables, you see tables, and under the hood, we write all of your data from your tables to 3 availability zones, making DynamoDB highly available by design. It also comes with data encryption at rest, where you can choose what level of control you want over the key that is being used for that encryption. It comes with fine-grained access control with AWS IAM and resource policies. If you're already using AWS, those should be very familiar to you. It has multi-writer global replication, When you create a DynamoDB table, you choose the AWS region that you want your table to exist in. If you want to, you can choose to extend that table into other AWS regions. Amazon will deal with replicating your data to those other regions, and then you can read and write to any of the regions where your table exists, and DynamoDB will deal with replicating those changes into your other regions. And all of this is backed by an SLA. 4 nines if your table exists in a single region, 5 nines if it exists in more than one region. DynamoDB is also serverless. We speak to customers all the time who have need for performance at scale, but there are some customers who don't need performance at scale. Maybe they don't need it today, maybe they won't need it ever, but we still see those customers choosing to use DynamoDB because it's truly serverless. What does that mean? There's no infrastructure for you to provision. You don't need to think about clusters. You don't need to think about instances or instance sizes. You don't need to think about instance placement or readers and writers and replicas. You just create tables and you work with tables. Those tables can come with automated scaling. They will scale up to meet the needs of your workload, and they will scale down again. If your tables scale on 3 independent dimensions: read throughput, write throughput, and storage. If any of those scale to 0, you pay 0 for that dimension. There is no maintenance windows or version updates. You won't have to go through upgrade cycles again if you use Amazon DynamoDB. If a new feature comes along, we just add it to the API and it's ready for you to consume. And if you don't want to think about read throughput and write throughput, you just want to have a table, you write to that table, and you read from that table, and Amazon bills you for what you actually read and actually write, you can have that with on-demand tables. DynamoDB also comes with built-in integrations with other AWS services. A database doesn't have to be a standalone component. It can contribute more to your architecture through native integrations. DynamoDB has too many native integrations for me to cover in any detail in the time that we have today, but here are a few highlights. Logging, monitoring, and analytics with Amazon CloudWatch, AWS CloudTrail, and Amazon CloudWatch Insights. Change streams through DynamoDB streams or through native integration with Amazon Kinesis data streams. You make the configuration to have a data stream, and every change that you make, the data in your table will just appear in that stream, meaning that you can do things like event-driven architectures or notify downstream systems, or just write those changes to somewhere as an archive perhaps. It also comes with 0 ETL integrations for other AWS databases. So if you want to leverage the strengths of Amazon OpenSearch or Amazon Redshift, you configure 0 ETL and Amazon will deal with replicating your data into those databases so that you can take advantage of your data there. And lastly, we have import and export data to Amazon S3. With a simple API call, you ask DynamoDB to export your data to S3. DynamoDB will do that with no impact on your tables, and once your data is in S3, you can do whatever you wish with it. So that's a short tour of Amazon DynamoDB, and with that I'm going to hand back to Jamie and ask, we've heard about Trainline, we heard about some of your challenges. What did the Trainline do and how did you do it?
Thanks, Chris. So what have we learned along the way? So I guess the first point is you really need, I can't overstate enough how important it is to really understand your access patterns, how data is used and how it's accessed. It's critical to make the right decision when choosing a technology. You also need to relook at your architecture to really get the full benefits of this technology. We found that moving from SQL has meant that we are using different database types for reads and writes, for supporting complex search, for data management, and for analytics scenarios. You can also significantly reduce the development effort you have to invest by using the out-of-the-box integrations and capabilities like auto data expiry. Like Chris mentioned, we found that about 80% of our use cases are looking like they're going to be moving towards NoSQL. I also can't emphasize enough the need to be able to invest in engineering enablement and the required shift in thinking. Getting NoSQL database design right is challenging, and engineers need to unlearn a lot of the things that they had previously learned when using SQL Server technologies. AWS support and training has really helped us with this. Finally, data migrations is always challenging. Moving data is hard, especially mission critical databases with zero downtime requirements. It's also costly, so looking at costs and factoring those into projects is really important. I'm going to walk through a simplified view of our orders migration and how it's been improved by the adoption of AWS technologies. After working in commerce for around about 10 years and seeing this in various other companies, this is pretty much a go-to design, built upon a combination of event sourcing and CQRS patterns. It's architected around three subsystems. The first one is order processing, where each action on an order is captured as an event and stored in an event record in a database. So they're things like order creation, payment taken, train cancelled and rebooked in our case, and ticket issued. All events are then fired into the order projection service, and which uses all previous events to calculate the current state of an order, and that is updated within the order projection database. Finally, all of this data is taken from the order projection database and added to a search index to allow customers to be able to get access to their tickets by order ID or customer ID, or for complex search scenarios in the contact center. So walking through the previous implementation, where are the problems? So the first issue is the SQL Server instances that are masquerading as queuing technology. That's just additional database management overhead. The next thing is around within the order processing and order projection. It needs to write to both the transaction database and to the event database to be able to move on to the next step of the architecture. And failure scenarios, sort of outages between those services, can lead to the platform being in an interim state, which all need to be engineered and handled. Problem 2. These transactional databases and projection databases are huge databases now in our world. Built on SQL, they're just complicated and difficult to scale and manage. Problem 3 is this order search database, which is a complex search database built on Microsoft SQL Server. The indexes in this database are 3 times the size of the data stored within them. And all this is fine at a certain scale, but as it increasingly struggles as data access volumes increase. In our case, this was significantly compounded as we introduced more real-time experiences into the platform, where customers and our systems were frequently checking the status of orders to understand, in the event of train status updates or disruptions, which customers needed to be notified. So here you can see the new simplified architecture leveraging the native capabilities of DynamoDB and its integration into the AWS ecosystem. There's a single write to the order transaction database, and we're using Amazon Dynamo Streams to be able to pick up all those events and move on to the order projection state. The order projection state gets all the previous order events, recalculates the state of the order, and saves that into the order projection database. We've taken the opportunity here, because DynamoDB is such a scalable platform, to move all the customer interactions by customer ID, order ID onto this order projection database, which improves the scale of the platform. And now we're using DynamoDB streams to pick up those updates and publish those into the order search database. And now with only 7% of order access left on this order search database, handling all of those more complicated order queries, we can downgrade this into from a mission critical database. We're also considering using zero ETL to reduce the amount of code further here. Chris, that's our architecture. Can we look at a DynamoDB implementation in a bit more detail?
Absolutely, yeah. Let's take a look at what that would look like as DynamoDB tables. So I have to emphasize, this is not Trainline's tables. This is purely fictional, just so we can cover the concept and look at that. So DynamoDB, just like every other database that I've ever worked with in my career, you have a table and you put records into that table. We call those items in DynamoDB, and every one of those has to have a primary key, and that primary key has to be unique. In DynamoDB, for this table, we've got 2 parts to our primary key. We have a partition key and a sort key. For the partition key, I'm using the order ID, And the way to think about a partition key is the value will tell DynamoDB which storage node this item should live on. The second part of the primary key is the sort key. For that, I've used the date and the time of the event that is coming in. The way to think about the sort key is it tells DynamoDB how to order these items under this partition key on the chosen storage node so that we can do some efficient retrieval with them. So that's our primary key. Alongside the primary key, we have additional data. If you're from the relational database world, think of that as like the columns in your relational table. We call those attributes in DynamoDB, and you can see here for this table, I've got two attributes. I've got the event type, and I've got some additional data that came in with that event. We've then got 5 events in this table, and that's split across 2 orders. So the first order begins with the order ID ABC, and the second order begins with the order ID XYZ. There's 3 events for the first order, there's 2 events for the second order. So now we want to work with that DynamoDB table. So we're going to look at some of the operations that you can perform. So the first one is get item. Kind of self-describing really. You provide the primary key, and then that's going to return 0 or 1 items depending on whether or not an item exists with that primary key. So you can see here on the slide we've provided the order ID and an event date time, and we're going to get back a single event. This operation is single-digit millisecond latency at any scale. This is what Amazon was doing for 70% of its operations on its relational database. The next operation that we're going to look at is called query. This is a super powerful operation in DynamoDB. We provide the value for the partition key. So in this case, we're going to provide the order ID, and that tells DynamoDB which storage node to go to and work with. And then optionally, we can provide some detail for the sort key. So we can provide a condition to get back a set of items, or we can say nothing at all about the sort key and get back all of the items that live under that partition key. So in this example, I've provided the order ID, that's the partition key, and it's going to return all of the events for that order from the table. This is also millisecond latency at any scale, and this is what Amazon was doing for the other 20% of its operations. So tables are great. We can now read from those tables, but of course we have to be able to get some data into those tables. So the next operation we're going to look at is called put item. Again, really well self-describing. We can put a new item into the table. So this is going to be single-digit millisecond latency at any scale. We choose our data, we choose our primary key, and we're going to write that into the table using the put item operation. As Jamie was covering in the Trainline architecture, if we've got a DynamoDB stream configured for that table, once that write happens, that item gets inserted into the table, we're going to get a corresponding event in our change stream. And you can see that on the right-hand side of this slide. So this is a JSON payload that appears in your stream, and it contains plenty of useful information. For example, it will have the event ID so that you can uniquely identify this event. It will have the event name, which will communicate whether this was an insert, an update, or a delete. And it will have other metadata like the approximate creation date time of the event. It will then also contain some additional detail. So it will contain the primary key of the item that was affected, so you can go and look at that item. And then as a customer, you can choose what additional detail you want. Do you want to see what the item looked like before the change, what the item looked like after the change, or do you want to see both before and after? With a configuration change, you can choose which one of those 3 you want. And then again, just like in the Trainline architecture, you can configure Lambda through a native integration to consume the events from that stream and apply your business logic. And with that integration, you don't have to get involved in spinning up infrastructure or scaling. Lambda will deal with that for you. So that's the events table. But Jamie also mentioned an order projection table. So we can see here on the slide, we've got the events table at the top with a DynamoDB stream and a Lambda function consuming that stream, and then it's going to create the order projection. So inside the stream, we're going to see the primary key of an event that has occurred. We can use the query operation to go to the events table and retrieve all of the events for that order, and then apply our business logic to create a current view of that order, so we can roll things up and put all the detail that we want. And we can see that in the bottom right table here, where we've got 2 items, one for each order that was in the events table, and it's showing the current state. So I've worked with customers in the past who've had a table for something like orders or products or something like that, and they want to make changes to the data in that table, and then they also want to store an audit log of the changes that were made, why, by who, and how. With this pattern that Jamie has shown us today, that problem's solved. We've effectively inverted it. The events kind of are our audit log, so that problem is solved for us. So Jamie, I wanted to ask you a couple of questions about your architecture, actually. I think what I've just shown here is basically the event sourcing implementation. But earlier on you mentioned CQRS. Could you tell me a little bit more about what that is and how it works here?
So CQRS is Command Query Responsibility Segregation, and it's really about separating your reads from your writes. So in our instance, actually the first part, the projection into the orders, is a sort of CQRS, but the more traditional pattern is when you're publishing the order projection, which is all of the data into your search index, and that is a publishing to a read view.
And you say you see this kind of pattern before. So if I was to say, I'm sure lots of our customers are used to the idea of stock and warehouses and that kind of thing. How would that apply with this kind of pattern?
Yeah, I mean, event sourcing is a great implementation pattern for the stock management systems, where you might have an online platform which has got a up-to-date view as far as the customer's concerned of what stock's available, and all the time that's changing. Products are being added to basket, or people start checking out, and then they might expire as they go out. So you're constantly recalculating the current state of your stock levels. But somewhere in a warehouse somewhere, they'll have an overnight process where you'll be going through and doing a stock check at some point in the morning, like more than likely, and then maybe an hour or two later, you end up getting all of that sent from the warehouse management system into the online platform, where you've got to go back and recalculate the stock view from the point in time where that stock view is taken. And that works really well, because within the event sourcing pattern, you might have an hour or 2 hours of increment, decrement stock, people checking out, people expiring those events, and you can replay and recalculate your current stock from exactly the point in time when the warehouse stock check was taken.
So I could ask you a million more questions. We could be here for hours because it's such an interesting pattern, but I think we need to get on. Could you tell us a little bit about what's next for Trainline?
Okay, brilliant. So what has all this actually meant for Trainline? So the first thing is that we're really seeing an improvement in reliability of our platform. We're seeing it more as we move to the cloud native databases into DynamoDB and AuroraDB, that it is causing our platform to be more stable. We're also seeing that our database engineering teams are spending less time managing the infrastructure, and so are able to be more engaged with our product engineering communities. So they are more proactive in supporting the platform and making it more scalable, but they're also able to work with our product engineering folk on coming up with new and more innovative features for our customers. And then finally, we're also starting to see a 20% reduction in the cost of our databases and database-related infrastructure, which at our scale is a massive win.
Awesome, right. Well, thank you for that, Jamie. So there's a QR code and a link below for those of you who are interested in exploring DynamoDB a little bit more. That'll take you to all kinds of interesting resources. And the last thing from me is just to say thank you to Jamie and Trainline for taking the time and energy in investing into this to share this story with everybody out there.
Thanks, Chris.
Thank you.